guys, today we will try to finish everything already. As calculations, now we have talked about the calculations being, just to review again, right? In titrations, okay, there are two types of titrations, acid, base, which we have finished, and second is redox. See, in acid and base, it's not redox. It is just neutralization. Why? Neutralization. Because basically in this reaction is basically acid plus alkali. Water is it. So there is no change in oxidation states. There's no transfer electron. Hydrogen is +1, oxygen is -2, is hydrogen is +1. So it's +1 and here's -2. So there's no change. No change. What? In oxidation number of states. But in this reaction here, there will be change. There will be two reactions. One is oxidation and one is reduction. Okay? So how many types of redox titrations will you have? Basically, we are dealing with two. One is with KMnO4, acidified. This is the main one. Okay, this is the main one. You have plus something else, plus something else. Okay? So the second one, of course, is a thiosulphate, sodium thiosulphate. Okay, and normally this one will react with iodine. Right? So we will see these two kinds of reactions. Okay, now let's go to straight away. I want to show you the theory. KMnO4, right? KMnO4, of course, you know the KMnO4. Okay, here, potassium manganate 7, or potassium permanganate. See, 1 mole of KMnO4, which is purple in color. Okay, should do this, right? Of course, if you ionize it, remember this is ionic substances, give you K plus and your manganate ion. You know this whole thing is 1 minus, oxygen is -2, so it's obviously +7 now. Okay, this purple color, right? +7. So 1 more here gives you 1 more and 1 more. So here we just, because K plus has no color and it won't take part in the reaction. Why? Because it's completed octet. It's 2, 8, 8, is it? Because K is 2, 8, 8, 1. So it loses this one here to become K plus. So now this is your +7. This is a very powerful oxidizing agent. You learned in Form 5 already. It's a very powerful oxidizing agent. Which means what? Which means it undergoes reduction. It means it's able to take electrons. It loves electrons, so it will take 5 electrons. From where? From where? Must come from somewhere. We will come from substances which are reducing agents. Okay? Okay, now we see here what are some reducing agents? Fe2 plus, common one, very common Fe2 plus. Okay? Also, this one here. Okay, it's an ethane diuate ion. I show afterwards, okay? And of course, sometimes hydrogen peroxide, and sometimes tin, also can tin SN2 plus, whatever, okay? So you've done that before in our calculation of redox reactions. Now here, basically it's iron, okay? Now, which means for this purple color, see, if there is no electrons coming, it will stay purple. It will stay somewhere, it will not react. But if there's somebody giving electrons, it will react, okay? But it always react with in the presence of acid, and this acid must come from H2SO4. Because if it's HCl, the Cl minus can be oxidized by your KMnO4 minus, so you don't have any side reactions, okay? So this H2SO4 is quite stable. So for 1 mole, see, Mn2, Mn4 plus Mn7 plus, or plus, 7 plus, okay? Right? 7 plus, right? It's going to something like that. Now, actually, this is colorless, or very faint pink, but not quite colorless, okay? If it's a reaction, it will, KMnO4 will be decolorized, okay? So there's 2 plus here, I don't know, or normally this got this, well, we normally say it's +7, you ask for oxygen state, so it's +2, okay? So for +7 to go to +2, it's a reduction, isn't it? So it must contain 5 electrons. So 1 mole, that's it, 8 moles H plus, and must have also 5 moles of electrons. Must have, okay, for this reaction here. So of course this follow reaction is called what? It's reduction. So it can only happen if somebody were to supply this one here, supplied by somebody by a reducing agent. Okay. So who's the reducing agent? So in this first titration here is Fe2 plus. Okay. So we know that Fe2 plus 1 mole, right, can be easily oxidized to Fe3 plus. It's quite an easy reaction. It means if it goes here, it means it plus electron here. It means it comes out. Sometimes books will write Fe plus minus 1 electron. This is okay, but even markings they put it, but I prefer to put the other way. Okay? This one comes over this side. Okay, so plus here, that means 2 species here. So in 1 mole gives you 1 mole, gives 1 more electron here, but here it requires 5 moles. So how? So for 1 mole to react, it needs 5 electrons here. So how many Fe2 plus react? Of course, 5 times 5 times 5 times 5. That's why here, right? F is right here. I'm going to put red color now. So you can see here is 5 moles, right? To give you 5 moles and 5 electrons. So ngam balance and unbalance. So you add, of course, this is oxidation. So you add the whole thing up, you cancel the 5 electrons, and you get 1 mole Mn for 8 mole. Now it's very easy to remember this 8 here. Why? Because from water, isn't it? Here got 4 oxygen. That means from water H2O, it must be 8, isn't it? Quite simple to remember. Right? So of course here I got wrong. I'm sorry about this. Maybe 4 here. Typo error. 4. So add over here. Here is 8 plus 5. So it's on this side. Reagent side. So here, Mn2 plus, arrow here, plus 5 moles of Fe3 plus, okay, and your 4 moles here. So the idea is, in this case here, one mole of Mn, 1 mole here will react with 5 moles of Fe2 plus. How do you do this in exams? Okay, now quickly, let's go to the question. Okay, question is 52. This comes up for your paper 2 as well as practicals. Okay, so you must be careful. Okay, the commonest form of iron 2 sulfate is the hepta. Hepta means 7 heptahydrate. Okay, given here. Right, F is 4 dot 7H2O. On heating 90 degrees centigrade, this loses some of the water of crystallization to form a different hydrate form of Fe, iron 2 sulfate. You see it. So X, you don't know how many moles of your water is lost. Okay, so you just put X. So it says now 3.40 grams of iron sulfate XH2 was dissolved in 250 solution. I told you, a picture paints 1,000 words. Yeah, I think I can draw up here. Okay, so here you got. Okay, this is your FeSO4 dot XH2O, and what's the mass equals to? 3.40, and you put it into 250. Okay, it's a standard flask. You will see all this later when you do a practical. Okay, you have to know what they are, but there's a line here. So you put inside here, and you put water inside here, and it becomes volume here equals to 250. Very important. Okay, inside here to dissolve. Okay, it's a very soluble substance. All right. Okay. Now from here, a 25 cm cube of this sample, this one here, was taken out. Okay, and you put down here. Okay. So here, the same solution as here. So here I put V1 now. V1 goes how much? 25.0. Now I'm going to use a pipette, is it? And this one will got, of course, got the FeSO4, right? Right? Forget the water because the water has already dissolved. Okay? And now you titrate what? use KMnO4. Well, see, example, titrate with KMnO4. Yes, right. And KMnO4, the molarity is equal to what? Molarity M2 is equal to 0.0200. Remember, let me say one this accuracy here. 4, 3 sig figures here. 4, you count the first one here. Molar. Okay? In this titration, 20.0 cm of this KMnO4 was required. But to react completely with iron 2. That means the volume here used for complete reactions, how much? 20.0 cm3. Okay, right? So you see the pictures already. Alright, now then they ask you the MnO4 minus is potassium 7. Why 7? Because it's plus 7 plus. Oxidizes Fe2 plus in the acid. Oxidizes means change to Fe. Explain in terms of electron transfer. Remember electron transfer, they want this a bit of oxidized, okay? It means it's when electrons are lost, okay? Electrons lost. Okay? A reaction and a reaction. Where? Okay. Right? That's oxidation. Now here, complete and balance the other equation for the reaction between the magnetic ions. Easy, isn't it? So if you look at, if you know the theory which I explained to you just now, right, you can actually derive it up what you want to. But this is okay. So how many moles? Here, 1 mole. Moles with 5 moles. Okay. Okay, so we can see it. Right? 5 moles here. But also you can actually know how to balance. Very simple. See? If you look at it, if you're smart, I'm sure most of you are smart. Half of you are smart, half of you are gurus. This is 7. This is what? This is 7 plus here. Right? And here's, of course, you have to know here, right? Here's Mn. You have to know. What we cannot do. Okay? So from here to here, you have what? Has gain plus 5 electrons here. Okay? Right? So Fe2 plus Fe3 plus from here to here. For one of them, you will have to lose 1 electron. So 5 then, 5 minus 5 electrons. So they cancel. Right. So remember the 4, right? 4, let's say 4 here now. Because it's only place again oxygen. Okay? So it's 8. So it's 8. Easy, isn't it? No problem, man. Okay. Calculate the number of moles of MnO manganate. Okay? This one is MnO4 minus use of simple. What? Number of moles equals to what? And same over thing now, over 1000 here. Okay? Equals to molarity you given here. Right? So you look at here, this is the one that you need to use. Okay? 20 and 0.02. So it's 20 or 0.02 first, 0.02 times 20, 1000. Okay? Cancel times is 4, so 1, 2, 4 here is 1, 2. Okay? 4 here is it. 0.4 is 1, 2, 0.003. Let me check. Yeah. So 0.04, so 0.0004 moles. Okay, from this equation, A2 and B1 current number of moles of present in 25 cm3, okay? Because the original was 22 to 50, isn't it? So of course you use the ratio, the number of moles. So the number of moles of Fe2 plus over the number of moles of MnO4 minus. What is it? There here? Given here, right? 5 over 1 is it? So it's 5. So it's 5 over 1. So number of moles of Fe2 plus is equals to 5 times what? 0.0004. Okay? It's 20, so it's 0.002 moles. That's not. Right? In what volume? In 25 cm3. Now, make sure you know. Current number of moles of Fes is the whole thing in. Now, this is dissolved in where? In your 250, is it? But now, here are a few things I need to let you know. See, this is Fe2 plus. So you can see that first equation. FeSO4, okay, will give you Fe2 plus SO4 2 minus. So here's 1 mole is to 1 mole is 1 mole. That means 1 mole came from 1 mole. Yeah. But 2, this is very important. I mean, it's very simple, but it's so important because 2 is stoichiometry and it's how you find X. So FeSO4, fan is blowing and making a lot of noise. So I put away first. Dot XH2O gives you FeSO4 plus what? X moles. Right? Yeah, it's very important. See? So 1 mole of this whole thing come from, give you 1 mole. Isn't it? Yeah. Yes? Yes? So you can actually say, right? You can actually now relate. I've got a blue pen, blue color. So I want to relate this one here, right? This one here with this one here, can, is it? Right? I'm going to show you some later we talk about this, okay? I can say that FeSO4 is equivalent. Number was, it's not the same, but it's equivalent to this one. Okay? So 1 mole is to 1 mole. And from second equation, this first equation. Second equation, FeSO4 dot XH2O is also equivalent to FeSO4 now. Yeah? 1 mole is 1 mole. Therefore, I can also relate. I put a green color now to very nice. This is very nice. Okay. This one with this one here. Why I want to do this one? Because see this one. And we calculate it is this one here. So to make it easier for us, I can say therefore, right? I can put FeSO4 is equivalent to 1 mole of Fe2 plus is equivalent to, right? Yeah. 1 mole of FeSO4. So, right? See? Right, because this and this is same. So I can say now, I can say here, well, I can put down here FeSO4 dot XH2O is equivalent to number of moles of Fe2 plus, right? So the number of moles of, I better put red now, I cannot see it. The number of moles of Fe2 plus, okay, in 250 cm cube, it will be 10 times this layer because 25 is this one here. So for 250 cm cube, how much is 10 times this, which is how much? 0.02 moles. Yeah. Okay. Now, therefore, I can also say the number of moles of FeSO4x H2O is also equals to how many moles? Same, 0.02. Sit down. Cannot write really. Go back again. Okay, 0.02 moles. Yep. Okay. So now to find the relative molecular mass, obviously, you know that number of moles equals to what? Mass over mR. So number of moles is 0.02. What's the mass used? It's on here. Remember this of the whole thing. So I need to put the whole thing here. Right, the whole thing here. Right? It's equals to mass is 3.40. Very bad handwriting over mR. So mR is equals to 3.60 divided by what? 0.02. You find it out, which I did by myself, of course. It's equals to 170. That's the answer. Okay, now the last part here. The relative molecular formula mass of anhydrous. Anhydrous means what? No water, as in it? Okay, it's equals to this one. Okay, which means that this one here. So FeSO4 is our anhydrous plus the water here is equals to how much? is equals to the molecular mass is 170. Obviously, this whole thing, they do it easier for you, lah. They count easier for you, so you don't have to do again. Plus, now X, X moles now. Now, what's the MR for water? 18, of course. 16 plus 2 is it? 170. So 18X is equals to, that minus that is actually 18.2. So what is that, Kazuo? 1. This is 1. Simple, is it? Okay, now that's how you do. It's all titrations, but it's just has got, the titration is on redox reaction. Now quickly next one, okay? Page 50, I think it's page 50. Right? I'll show you the question first, then look at the theory here. Page 50, here we are. Right, at this one. Okay? 6.30 sample of hydrated mixed water, ethane uric acid. This one here. Now, I think I showed you before that day. This is called dibasic acid. Okay, it looks like this. Okay, I will review again. Okay, it's got 2 functional groups here. Okay, join another carboxylic acid group. Okay, 2 hydrogens. Okay, let's do again. We got H2. No. How many C? 2C is it? 2C O 4. Okay. This is called ethane. Why 2 carbons? Ethane. Why ethane? Because it's got 4 bonds. Okay. Ethane D. Di means the OH is for your carboxylic acid. But it also can be sodium ethanoate. No. Also can. Also can, because this one will give you 2 Na plus and of course your iron here. Now this iron is the one that will undergo reaction. Okay, right. This is the one, which is this part here. Okay, sorry, until this part. Now I won't go further. Okay, dissolve solution and make up. Okay, which means if you draw the diagram, which later I'm going to do for you. Now let's look here first. Now this part here. Okay, so maybe go here first. Right, so I've got here. Okay, I draw the diagram first. Here is our substance. What substance here? So your ethanoic acid. Now this is a solid. Okay, it's a big compound. H2C2O4. X the water of crystallization. It's called the water of crystallization. Okay, the mass is equal to how much? 6.30 grams. Okay, now you put this into and dissolve it into what? Into 250. This 250. This volume is equal to 250. Okay, CMQ. Put that here. Okay, and then they say that you draw from here, draw it out from here, and you put into a conical flask to here. You got now V1. How much do you drop? 25.0 cm3. Yeah, right. And then this was acidified. I put some acid inside. Why? For your KMnO4. No. You put acid H2SO4. Excess. You do this when you do your practical. And you titrate this with KMnO4 here. So KMnO4. Okay. So I say this is a famous redox reaction. Okay. And how much use? 20 cm, 20.0. Okay. So the V2 is equal to 20.0 cm3. Okay. Right. Required to this thing oxidize and so forth. Okay. And what's the molarity of KMnO4 given up? Earlier is given here. See? Right. Here is what? 36 figures, 0.100 molar. Okay. Same thing again, electron transfer. What the oxidize means, same. Electrons are being lost. Okay. Now here, how do you balance it? They always ask you for the final equation. This is called the final or the overall equation. Okay. I explained before. So overall equation or the redox equation. Now let's go back to theory here. All right. Now, see. The first one, of course, now this is, I put times 2 here because originally this is 1 is there. Okay, right? It's 1 mole with 8 moles in it. Okay, now I'll put that for you. Originally it was MnO4 minus plus Y8 because 4 oxygen 8H plus Y5 because this is 7 plus and it's going to go to Mn what? 2 plus now. 2 plus here. plus of course water is 4H2O. Yes? Alright, now this further here, your ethane duet ion here, C2O4, okay, the raw form, 1 mole of C2O4, 2 minus here, will become carboxylic acid. 2 moles. And there's charge 0 here. So how many electrons have lost? 2 electrons. So 1 mole give you 2 electrons. So if you want to react this with this, remember this is your reduction. So this is your half ionic equation. Half ionic equation. This is your what? This is reduction, is oxidation. Okay? Again, half ionic equation. Okay? So 1 mole give you 2 electrons. 1 mole needs 5 electrons. So how to balance 5 and 2? Common factor. I make 10, isn't it? So I times this one by what? By 2. I times this one by what? By 5, isn't it? So times 2, it will be 2 here, 16 here, 10 electrons here, and 2 here, and 8 here. Clear? Right? Now put a blue color now. Blue color. Now, right? So if I times this one here by 5, with 5 here, 10 here, and 10 electrons here. Why? To balance off this one. So now these 2 equations come together and give you this. This is your redox equation. Or this is called overall equation. Overall equation. Okay? It's redox. Why? Because one is oxidation, one is reduction. So I put 2 moles of this one here. Well, 5 moles of your ethane duet ion, 8 moles of H plus, and blah blah blah. So of course what I'm interested is this further here and this further here. Okay? Right, now let's go back to the question again. Okay, so now you can see it. So if you don't have memorized, it's quite simple. Right. Okay, so of course it's carbon dioxide here, of course it's Mn what? Mn 2 plus here. Okay, so the overall equation, now of course you must balance off the water first. Okay, you got some brains here. They get 2,5 already. You know, here's 8 oxygen. Here's how much? Here's 20 oxygen. So it's 28. You know, 28 oxygen, right? 20 oxygen. 20. Okay, 20. Okay, this is 8 and this 20. Yeah. Okay, don't mistake the here for oxygen. Here's already 20. So here be 8, isn't it? That's not. If 8 here be 16. That's not. Because 8 times 2, because there's no other type of hydrogen. So it's very easy. Don't remember anything, just use your brains. So if you have any, that's good. If you don't have any, just too bad. Okay, same old thing, calculate the number of moles of Mn. I told you always put the subscript here so you know what's happening, okay? MvO1000. Okay, Wes, now remember, go back to here, you can see. Oh, this is the thing I'm going to use. 20 and 0.1. Okay, so molarity is 0.1 times 20 or 1,000. Yeah? Okay, so let's move 1 here, let's move 1 here, and move 3. 0.002. Right? 0.002 moles. Okay, check my answer, correct. Sometimes it's very tricky one. Use the equation in A part 2 and B part current number of moles. Remember here is 25, right? For this one here is what? 250, isn't it? So you must remember, times 10, you know. Okay, for 25 is the first part here. So I've got number of moles, mole ratio, over number of moles of what? Of MnO4 minus. Okay, from equation how much here? You can see from here, on top here, 5 is to 2. So it's 5. What's on top of it? Over 2. So number of moles of C2O4 2 minus equals to 5 over 2 times 0 times 0.002. Cancer is 0.001. Of course, it's 0.005 moles. So for this case here, from here to here, right? Now, of course, here you can see Right? I told you before, isn't it? Right now, like here, the mole ratio H2C. This is the whole damn thing, the whole thing. C2O4 XH2O, right? Will give you what? Will give you H2C2O4 plus XH2O. Or you can see H2C2O4 will give you what? 2H plus what? 1 mole of what? Yeah. Yes. So 1 mole is to the whole thing, to 1 mole. 1 mole is to 1 mole. So from here, I use a blue thing again. Blue. So, okay, blue. So here 1 mole of this whole thing, same as 1 mole of this. Okay. So you can say here, if you want to put up, you don't have to. Okay. H2C2O4, right? XH2O is equivalent to what? What? C2O4 2 minus. Okay? So therefore, from here, right? So this is the whole thing, right? Plus water, here some water, right? So the number of moles of H2, I put the whole thing, so it reminds you XH2O is equal to the same, which is 0.005. Okay, so of course the mass is here, so how you find the so here. Okay, from here you can find is equal to 0.005 times what? Times 10. That's not. Why? Because it's in 250. So equal to 0.05 moles. That's not. Okay? This is 0.05 moles. Now, next step here. Okay? Remember this formula mass now. Okay, you're talking about this. Okay, so quite simple, right? So remember, number of moles equals to mass over mR. So what's the number of moles? In your 250 cm solution which contains your 6.30, isn't it? So 0.05 equals to the mass. How much is the mass? 6.30 over the mR. No, of the whole thing, the whole damn thing plus the water, no. So mR is equals to, right, 6.30 over 0.05. I worked it out and it's equals to 126. Okay. Okay. So now, yeah, of course, as you find X, quite simple, isn't it? Right? Formula mass of anhydrous. They give you just the last time, okay? Right? 90. So of course, you can put down there H2C2O4 XH2O is equal to how much? 126. So this whole thing is equal to 90 plus X times 18. Same as it. Same sort of calculation, is it? Right? So 18X equals to that minus that. Okay, which is 36. X equals to 2. Easy peasy, is it? Okay? Alright? Right, now I've thought I gave you 2 types of FeSO, your KMnO4 titration. Okay, you can practice it. The same thing about these two problems is KMnO4 is the titrating agent. Okay, and both of these reactions here, right, are redox. Of course, I'm going to say here, right, KMnO4. Now, KMnO4 can also react with your hydrogen peroxide, okay? Right. But when you do this equation, it's a bit hard to get to the result. Okay? So remember, the key thing is this further here, okay? This further here, okay? And this with Fe2 plus also is this further here. Okay, all right? So let me save this first. All right, save this. Let's say we go to D, AS, practical, zoom here. Okay, now let's go to Thiosulphate, okay? Thiosulphate, all right? Finish, Now, I'll show you the what was the question first, all right? 66. It's all redox reaction, but it's just different. Now, remember, you have to do this in your practical. Okay, sodium chlorate is a bleaching powder. Now you learn this formula, this substance in your organic chemistry, so no problem. But you need to know that there's such a thing. Sodium chloride, of course, sodium here, right? Remember, this is 1 plus. Oxygen is 2 minus. So chlorine here is 1 plus. No, interesting there. Not always think always -7. Cannot be, because of the different. I told you, different in what? Electronegativity. It's an active ingredient in commercial bleach. The concentration of chlorate, right? It's called chlorate 1. 1 means chlorine is +1. What do you mean by titration? Okay. Now, again, picture paints 1,000 words. 10.0 cm cube of bleach solution was diluted. Okay, so you put down here, put a measuring cylinder, whatever lah. Okay. Here's volume is equals to 10.0. It means quite accurate. Okay. Cm cube. It's a bleach. You want to be more specific. Is your NaClO. Okay. And put into what? Put into a 250. This volume V1 is equal to 250. It means you are diluted, okay? How many times? How many times? 25 times, no. Okay. This one is diluted 25 times. Remember, after it's going to go back once, okay? And then here, okay, 10 cm, dilute acid is put into dilute acid and excess of 2 things here, H2SO4. You do this in a practical, and your Ki were added to 25 cm cube of the portion of this solution. That means here you take out here. How much take out? Good night again. Okay, you take out from me how much? 25. Okay, put on here V2. 25.0 cm cube of this solution, same one, okay, of your bleach. Of course, diluted up, right? And you put what inside here? You put 2 things here, H2SO4 excess, plus your Ki. These 2 are in excess. And they will give out iodine, no, see, to liberate iodine. It means blah, 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 all this here will give out iodine. And iodine is a orange yellow color or a brownish color, or dark brown, B-R-O-W-N, brown solution. Iodine. And then what you do? The resulting solution requires 20.8 and 0.1 of your thiosulphate to react with iodine produced. So this is titrate now here with sodium thiosulphate S2O3. Okay. Now you can see they show the direction. The first reaction, when your bleach plus your Ki, this comes from Ki, and your H2SO4 will give you iodine. See now. Right? Now this is a balanced equation. They do it for you already. 1 Cl, 1 Cl, 1 O, 1 O. 2H plus 2. Iodine 2I. 2I minus 2. Now remember, right? Okay, this is, of course, if you look at it, is already a redox reaction here already. Okay, because it's +1 here, go to what? This -1. This -1 go to 0, isn't it? Okay, don't care. Right? So this is a redox reaction already. So here is one reaction number 2. The iodine given out here, I now titrate with thiosulphate. Also another redox reaction. Okay? What happens is it will react with something to give you. Now this one comes from, if you want to know, okay, say I2, okay, will be reduced. It will accept 2 electrons. Why? Why? Because group 7 got 7 electrons are the most shells in it. So they will take electrons. They are very good oxidizing agents. They take electrons. They undergo reduction. So 2. I minus with what? Originally 7. Then take 1 more. See now. So 2 take 2 lah. See? But this one come from where? Thiosulphate. Thiosulphate loves to give electrons. So it's a reducing agent. Okay? This is, of course, this reduction here. Okay, then of course the S2O3, 2 minus here, will go to, right? You need 2 to get S4O6, also 2 minus. Okay, so 2 times 2 minus 4 minus, so it lost 2. Okay, so plus 2 electrons here. So the whole thing, I put a red color now, to balance off, okay, 2 won't change. Okay, 2 electrons, balance 2 electrons, ngam ngam. So I don't have to times anybody. So it's 1 mole here, I2 plus 2 moles here, S2O3, 2 minus, goes to 2I minus plus S4O6. That's why you get some here. Okay, so, right? So now, very simple. All right? I want to relate, say this is the controlling factor. I didn't start with iodine, I start with my chloride, my bleach. Okay, my bleach. Everything is given in bleach now. Bleach. So how do I relate bleach to my thiosulphate? Very simple. Again, equivalent. So the first equation here, I'm going to put down B, okay? All right. From the first equation here, I can put equivalence. Let me see, 1 mole of ClO minus is equivalent to how many moles of iodine? 1 mole here, yeah? Yes. Second equation, number 2. 1 mole of iodine is equivalent to how many moles of thiosulphate? 2 moles of thiosulphate, yeah? Now, so this is common. So from 2 of them, I can get what? I use this is quite equivalent. You can check it out in your Google, okay? It's quite equivalent. Not equal, not it's equivalent. Okay? The number of moles is equivalent. So I can put ClO minus is equivalent to what? To 2 Si. Pani. Okay. To S2O3, 2 minus. So 1 mole is to 2 moles. Easy busy. Now I can put all my details down here. Remember, I put details here. So what is the volume I used for titration here? Right? See now. Okay, it's here, 25. So this V1 is equals to 25 cm cube. What moles of this do I use in my reaction? It's here? Yeah. So this V, what I put here is V3, isn't it? Let's put a second, V, see? Oh, I didn't put down here. Okay, let's can put here, the thiosulphate here. So V3 is equals to 20.80 cm cube. M3 is equals to how much? 0.100 molar. Okay, so let's put down here. Okay. Right. Remember, this is a thing here. So this is V3 is equals to 20.80 cm cube. M3 is equals to 0.100 molar. So to find the concentration, I want to find out M1 here. Okay, in moles per dm cube. There are a few ways to do it, but of course, SPM you do M1, V1 equal M2, you do M1, M2 can. But I want to do the normal way of your AS. They always ask you then to find here the number of moles here. Okay, okay. So the number of moles of S2O3 used in a titration, how much is it? M over V0. The same old thing, right? This is a better way because AS always go back to some calculation. In here, now here no step by step. They just up to you, freedom. Okay, but normally they give step by step like earlier examples, isn't it? Okay, 0.1 times 20.8 for 1,000. Here move 1. Okay, here move 1 here. Yep, you don't do this? Then here move 3. 1, 2, 3. It's equal to 0.0028. Oh, sorry. So easy to make mistakes, man. Okay, so it's equal to 0.0080 moles. Now this, remember, is found in what volume? 25 cm cube. Very important. This is found in 25.0 cm cube of your titration. Yes. Now it came from where? It came from here, this one, it came from here, right? Right? So here, that means the number of moles here is equal to times 10, okay? So in 250 cm cube equals to 10 times 0.00. Very important, this dilution factor thing. It's equals to 0.0208 moles. Now this number of moles of your chlorate, right? Moles is found in what original volume? Original volume. Huh? How much? See? 10, is it? So this number of moles is inside here. Okay? So the actual volume, so the volume found in what? In your 10 cm cube of solution. So with this, I put a blue again so that you can see clearly. So this whole thing now. Okay? Right? You want to find molarity, is it? Molarity is equal to what? Number of moles over volume, is it? So how many moles are there in your 10 cm cube? So 0.0208 in 10 divided by 1000. Remember, okay? You found this to be, something is wrong. Ayah, 2 lah. Why am I so stupid? 1 mole to 2. So I say something is funny. Okay, now this, now see, this is, sorry, now this one is a thiosulphate, isn't it? So remember, so the number of moles of ClO minus is equal to how much? 1 to 2, isn't it? Over number of moles of thiosulphate is equal to what? 1 over 2. Therefore, number of moles of C, that is quite difficult. Yeah, I mean, it's a lot of go up and down times the number of moles is 0. Here at first is 0.00208. That means it's equal to how much? 0.00104. Now this is in what? 20. Now here is wrong. Here is wrong. Okay. Here this one. Okay. You can go back. Doesn't matter. So find 25 cm cube. What? ClO. So for 250 cm cube of ClO, how much is it? Times 10, is it? So 0.00104 times 10. How much is it? It's equal to, this is all wrong, okay? 0.0 times 10, 0.0104 moles. Now this is found in what? In 10 cm cube. That's all. So the molarity is, so the molarity is equal to number of moles over volume. So how is it? 0.0104 divided by 10 divided by 1000. Okay? You work it out here, it will be 1.04 moles per liter. Because you cancel this mark, okay? So times 10, 100, move here 1, 2, isn't it? So it's 1.04 moles. Okay? Okay? Now for the last one. Okay? Now, of course, the indicator you use starch. Because at the end point, see, actually, sometimes don't need starch now. Because iodine, see, iodine is like dark brown. At first, very thick, it's dark brown. For iodine. So you titrate with thiosulphate. Thiosulphate is colorless. Colorless. So you go from dark brown to faint pale yellow. We call it lemon yellow or like the urine. Okay? And once the yellow is supposed to iodine. So as it reacts, it becomes less and less. Right? So normally, to see very sharp point, we put here, they always say 10 cm cube of starch. Okay? Which means this one will turn what? Dark. What? Dark blue. Okay? So it's starch here. Right? Instead, the color change we observe at the end point. So it's from dark, so blue to what? To colorless. Okay? Instead, when the procedure you will add, okay, when when the process you add iodine. Now, this is very important. No? You add it when it's pale, when titration. Because you put too soon, the starch will trap the iodine. Is pale yellow. Yeah. So they will ask you the procedure when you add the indicator. Okay, all right. Now next one, last one. Okay, we have 10 more minutes. Very good. So I plan my lesson properly. Okay, now you go into my theory. Is explained here as well. Okay, see, right? So there are many things you can write to liberate the iodine. Okay, right? One is iodate, came out before in the practical. Iodate plus Ki plus acid give you iodine. One is hydrogen peroxide, okay, plus H2SO4 plus Ki. These two are always the same. Now copper, copper 2 plus Ki alone give you your copper 1 iodide and iodine. Okay. This is the one we're doing now. Okay, copper. So they are the main titrating thing is a thiosulphate. Okay, like earlier, the main titrating thing is your KMnO4. Okay, now let's look at here. Right, now the last question is page 67. Okay, next page here. Okay, all right. Copper is used to make alloys such as brass. The percentage of copper in a sample of brass can be determined by dissolving the sample in concentrated nitric acid. The reacting mixture with Ki is used. Ki, which is your Ki, will give you your K plus and your I minus. This is where comes the iodine. Okay, 1.75 grams of the brass will dissolve in concentrated acid. Okay, the reaction of copper with brass with corn H2H and O3 with a brown gas, which is your NO2, and the green blue, which is a copper nitrate. Now they ask you here for a question, you won't know this. Okay, it's only done with the electric potential in your A2. What's this question? Is an A2 question or see? See, 42. So you can see AS question come in A2. Now, let me give you the equation, otherwise you cannot do. Okay? Okay, I'll just put the equation here. Right? So Cu plus 4HNO3 gives you Cu balance equation 2 plus 2NO2 plus 2H2O. Okay, 2 marks. How come 2 marks? First of all, if all the formulas are correct. Secondly, on balancing. Right? So now remember, you have here, if I draw a diagram here, this is your brass. Compared to copper, and the mass of the brass is 1.75 grams. Okay, you're going to put this into a solution here of concentrated HNO3. Okay, it's going to be a reaction. Brown gas given out. And left behind here is a copper nitrate. Okay, and then what happens is the resulting solution was neutralized to remove the acid, right? And of course, again, no juice already. Don't know why, don't care. Okay, right? That means this one here now is put into a 250 volumetric flask, which is this one here. Yeah? This volume here is 250, always one. Okay, that means he'll contain what? Your copper nitrate. Okay, right? You shake. Right? Then an excess of whatever other was added to 25% of this portion. That means you withdraw from here, the corrected flask for titration. How much you withdraw? 25. So the volume V1 here put is 25.07 cube of your copper nitrate. Okay, copper nitrate. So you can put all the details here you like. Okay, and then now what? The result solution requires 22.4 of 0.1 of the sodium thiosulfate. That means here is your sodium thiosulfate. Okay, be right here. sodium thiosulfate. And how much do you need to titrate to change to have all this reaction here? Well, V2 now how much is used? 22.40 cm3. And what's the molarity of this one here? 0.100 molar. Okay. Now they say they give you the reaction here. When you put copper, this of course comes from your copper nitrate. Okay. Which of course give you want to do the thing CO2 plus 2NO3 minus 1. So this one here. This one, the nitrate won't react plus the 4I minus come from your Ki. Okay. Give this one here. Okay. So this is given up. This one is a white PPT. Don't care. It's on here. So this is an excess. So the copper 2 plus amount here will be responsible for the amount here. Okay, so these two are as a relationship. Now then your I2 is titrated with your thiosulfate, and this is a relationship. So how do I relate copper with thiosulfate? Again, use equivalence here. So here, 2 moles of copper 2 plus is equivalent to 1 mole of I2. That's not. Here, 1 mole of I2 is equivalent to 2 moles of S2O3 2 minus. Therefore, how to relate this to this? Very simple. This is a common factor. I'm going to blue again. So this is a common factor. So actually I can put, if you like to put, 2 Cu2 plus is equivalent to 1 mole of I2 is equivalent to 2 moles of S2O3 2 minus. Or I can say 2 moles of Cu2 plus is equivalent to 2 moles of S2O3, just to have one semester, okay? Or 1 mole of Cu2 plus is equivalent to 1 mole of S2O3 2 minus. Now see they give you up to you. They didn't tell you what to do. Percentage of copper by mass. Okay, so now I want to find, well, how many in titration wise, what's my volume of sun use here? Okay, go back here. Here. 25. So V1 is equal to 25 cm3. How much of this thiosulfate is used? Here. So V2 is equal to 22.40. I hope I can see correctly. And your M2 is how much? 0.100 molar. So I want to find how many moles. Then I can find the mass, not number of moles here. Quite simple. So I start with known to the known. So the number of moles of your thiosulfate, very simple now, equals to MV/1000. Okay, what's M? M is 0.1. Okay, what is V? 22.40 over 1000. Okay, you calculate that out, it should give you 0.00, just make it fast, okay? 224 moles, okay? You can see here, okay, shift 1, shift 1, shift 1, shift 3, okay, correct? Okay, right? Now this is the thiosulfate. This is thiosulfate. Now how about copper? Same. So number of moles of copper 2 plus is same, 0.00224. Right? But this one is found in what volume? It's found in 25. But it came from 250Z. No. Yep. So you got times what? Times 10Z. That's all. So remember, this is found in 25 cm3. So for 250 cm3, how much is it? It will be 0.0224 moles of copper. Okay, right now this one came from where? Came from your brass there, all of them. Okay, right. So now what is? So can I find the mass of copper here? Right, this one is 0.02. Okay, so I want to find the mass of copper. So number of moles equals to mass over AR. Okay, yep. So mass is equal. This is 0.0224. Equals to mass over copper 63.5. So therefore mass is equals to 0.0224 times 63.5, which is equals to, I got it here, 1.4 0.224 grams. So percentage of copper in brass is equal to mass of copper over mass of your brass times 100. How much is it? Equals to 1.4224 over what's the mass of your brass you use? 1.75. Look up here. If you're not sure, look up here. Where's the window? Are there? 1.75. Okay. So times 100. A lot of maths, is equals to 81.28%. But they ask you in how many? 3, 6 figures. You please get wrong, no? So equals to what? 81.3. The marking sim must be this one here. This one is wrong. Okay? Look at here. Okay, now I finished. Okay, I finished everything already for your titrations here. If you look carefully here, we have finished all of part 1. Okay, all these things in detail. All right. So the next one will be I'm going to do is on well, the part 4. Okay, which is on well, the gas laws. Okay, because another teacher will take over 2 and 3. Okay, so I'll see you then. Make sure you do the thing again and again. Even I can make mistake. You can see it's all recorded down. Mr. is not very smart. Okay, I'm just very clever, right, to correct myself. Make sure you do it again and again, and you get a hang of it. Acid base or acid base or redox, or maybe it's gas, or maybe it's just solid here. You have to know how to do it. This one comes in for paper 2, paper 1, and paper 3. So I cover it quite deeply in a titration array. Okay, thank you very much, and bye-bye. I'm going to off this thing now. Off it.